Okay, so good evening, good morning, welcome, and thank you all for joining the webinar on the hydrologic modeling. I know some of you joined through Zoom and some of you are also viewing live streaming. So it's very difficult to come up with a number, how many people you joined, but we are seeing that lots of people responded and still started to pouring in. So thank you all for your time and effort. My name is Khalid, and I am working with the BUETAAA-An Alumni Association in Alberta, and I will be chairing this seminar. First of all, I'd like to thank BUETAAA Alumni Association in Alberta for helping me in organizing this seminar. There are lots of things going behind the scene to arrange such an event. Please note that we are unable to go through the registration process to make your participation. We haven't done it intentionally just so that you can easily participate with the code and the meeting number. But it's also important to know that we will be asking for your feedback because our plan is to continue those type of seminars which would be helpful for you. So your feedback and also communicate our next seminar with you folks. So if you guys can please write your name, institution, and the name of your institute and the email address, that would be easier for us to communicate with you. I am taking this opportunity to introduce the association very briefly before going forward to the main seminar. So BUETAAA-An Alumni Association is a social and professional network hub. It's started in July 2018, and some of the major goals is to act as a convener in promoting increasing knowledge shared among its alumni association, BUET, and other universities in Bangladesh, and also some professional organizations, and also to arrange social, cultural, and professional activities to foster growth among the association members. As a part of this goal and objectives that I mentioned, today we are organizing this seminar, and the title is An Introduction to the Hydrological Modeling with Python. We are very delighted to have Dr. Andrew Ireson today, as he agreed to contribute his valuable time, especially the family time. Today is the weekend here. So I sincerely hope that you will all be enlightened by his talk. I just want to give a little bit bio of Dr. Andrew Ireson. So Dr. Andrew Ireson is an associate professor at the University of Saskatchewan, Canada. He's a subsurface hydrologist. His research focused on combining field observation with models to conceptualize and quantify the process that determine the storage and movement of water and contaminants in the subsurface environment. And he uses Python every day for data analysis, modeling, and plotting. He teaches numerical methods using Python. Andrew received his PhD in hydrology from Imperial College London in 2018 and moved in Canada in 2011. And since then, he's working with the Global Water Institute for Water Security. He has a good number of high quality publications under his belt. His main research area is subsurface hydrology, climate change, and water security, land water management and environmental change, and sustainable development of natural resources. It's interesting because we haven't mentioned that to you. He is familiar with Bangladesh because I think maybe 10 years ago, I might be wrong, he went to Bangladesh for a project and talked with some of the universities. So he has some idea about Dhaka city. So without further ado, I'll let Andrew Ireson to start his talk. And at this moment, if you have any questions, then please write it down and put it on our chat. And then once Andrew's talk is over, then we will go for a Q&A session. I know it's 10 o'clock night in Bangladesh, so I don't want to keep you wait till 12 o'clock. So let's start. Thank you, Andrew. Go ahead.
Well, thank you very much. Salam alaikum, everybody from Saskatoon. Thank you very much for joining this evening. I realize it's quite late your end. So I don't really know who I'm talking to, but my talk is going to be targeted to, I think, students and grad students who might be working in the field of hydrology. So I'm going to be talking about hydrological modeling with Python. And I'm going to probably talk for a little bit less than an hour. Sorry, my mouse is slipping here. I'm going to probably talk for a little bit less than an hour. And basically, to summarize, my goal here today is going to be to introduce you to some of the things that you can do using Python. I haven't got time to teach you these things, but the idea is to expose you to them. And so that if you're not familiar with Python, you can get started. All right, so let's just jump in then. So today's objectives are to review what kinds of problems we can address using hydrological models, understand the opportunities that open source software, in particular Python, provides to us, give you the knowledge of how to get hold of Python and what packages you need and how to start, basically, in particular with the Jupyter Notebook interface. And then we'll demonstrate the steps in writing a very simple hydrological model from scratch. And then we'll play around with an existing model that's called the HPV model for a watershed in Canada. And at the end of it, I'm hoping that we'll have broken down some of the barriers to entry if you are not currently using Python or any other kind of scripting language. Hopefully that this will encourage you to try to do that and learn it yourself independently. Okay, so hydrological modeling. Obviously, we're dealing with the hydrological cycle. I assume you're probably all familiar with that. The classic problem, of course, is to try to simulate stream flow in response to precipitation, so-called rainfall runoff modeling, and that's really going to be the focus today. So why do we need models? Well, just a few words about this quickly. In hydrology, we can't measure everything that we need to know. And what we can measure, we measure very imperfectly. It's a very uncertain science. So measuring stream flow, measuring rainfall, measuring soil moisture, measuring groundwater, anything you can think of is very difficult to do accurately and in a representative way. So in a very general sense, we use models to try to extract information from from the data that we have that's imperfect and incomplete. And typically what we're often trying to do is predict the future. Okay, so in particular, what might happen to a river if we have changes in climate variables such as precipitation and temperature, or if we make some modification to the system, such as building a dam or building a parking lot or cutting down a forest or whatever it might be. So climate and land use modifications. And again, a classic problem is trying to predict the occurrence and magnitude of flooding. And in fact, our host today, Dr. Akhtar, this is what his professional work is all about in the province of Alberta in Canada. So there are two ways that we use models that are useful. The first is for predictive modeling, and this is what everybody thinks about when you think about modeling, using a model to make predictions about something. And a classic example would be a weather forecast. But another way that we use models that's less perhaps obvious is what we call explanatory modeling. And this is kind of using models within the process of fundamental research in hydrology. And what we're trying to do here is test hypotheses about how a hydrological system works. What do I mean by that? I mean, basically test our understanding of how a droplet of rainfall landing in a watershed moves through that watershed and out into the river and out, out of this watershed. So there are many different processes that are happening, and we have imperfect understanding of lots of these processes. And so what we can do is we can come up with ideas about how these things work, and then try to test those ideas using models and falsify the models against observations. That's kind of what my research is all about. So that's the motivation, modeling either for prediction or to explore processes. Now, why should you use Python? Well, before I talk about Python, let's talk about coding. Why should we use scripts and coding? Do we need to do this? Well, we do. In the modern day and age, it's essential that you have coding skills, both for the job market and also for careers in academia. So, I mean, a very simple answer why Python. If you learn how to code, you're going to be much more attractive to employers and potential supervisors. And the reason that you're more attractive is because when you can use coding, you can do things that other people can't do, and you can do them more efficiently and more effectively. We also have in science a reproducibility crisis. This is where somebody writes a paper and presents a result, but then somebody else tries to come back and reproduce that result and can't reproduce it. And one of the reasons that we have this is because people are not using scripts for their analysis. So if you use a script to do your analysis, anybody else can take your script and reproduce your outputs. And so this is really a strong onus now on everybody to both use scripts and share scripts that are associated with any of their conclusions. We're also dealing with large data sets nowadays. For example, climate model outputs, which are these huge gridded, spatially gridded and temporally fine resolution data sets. So 4-dimensional potentially. And this is way beyond the capabilities of spreadsheets to look at these data and plot them. So you have no choice but to use some sort of script to do that. Now, Python is a particularly good place to start if you're not already using scripting languages, because for many reasons. One of them is open source and it's completely free. So when I was a student, oh gosh, almost 20 years ago now, this wasn't available, and we had to use things like MATLAB, where you have to pay for a MATLAB license. But now these very, very high quality software is available completely free. So anybody can get it on any computer platform. It's relatively easy to learn, and it's extremely powerful. It does a lot. And in Python, you can do all kinds of things from GIS to numerical methods, and lots of very powerful data visualization. And it's continually improving because it has a large community of developers that contribute to it. I will just say though, even though I like Python, there's nothing wrong with other languages like MATLAB and R. So if you are started on those languages, you don't have to stop now, carry on. And the good news is when you've learned a language, the basic skills are transferable from one language to another. So yeah, it's fine if you're using a different language. Now, for most people, the way that let's say you're doing some modeling in your research or in your work, most people, the most appropriate way to use a scripting language or Python is what I call the Python model sandwich. So this is where you have Python as a pre-processor and a post-processor for your model. So pre-processing involves manipulating data so that it can be read by the modeling software. Just to give an example, the model could be ModFlow, or it could be Hydrus, or it could be SWOT, or it could be any number of models that are available. So those models need to sort of ingest, let's say, a time series of rainfall in a particular format. So you can use Python to generate that driving data file. And then you run the model, and the model will output something, for example, a time series of streamflow. And you can use Python to then load that data and manipulate it however you want, plotting it, calculating statistics, and so on. So for most people, most of the time, that's going to be the use case of Python. And for that reason, the best thing to do if you're starting out is to learn how to manipulate data with Python. That's the most valuable skill. We'll talk a little bit about that today. However, for some people, some of the time, as I put it, it's going to be useful to write a model in Python from scratch. Who would want to do that and why? Well, first of all, if you're a student and you're learning about modeling, you should really go through the process of understanding how a model is put together so that you get that critical insight into the kinds of assumptions that are in the models. And so writing a model in Python is a very good way to develop that understanding. And then researchers also might want to write models from scratch if they're doing exploratory modeling, as I mentioned earlier, because when you're doing exploratory modeling, you often want to test out new ideas very quickly about how the system works. And if you have a model in Python, you can do that very easily. Sorry, is that a question or is somebody just talking?
Somebody need to unmute, please.
Sorry, I think I muted that person. Okay, where am I? So basically what I'm going to talk about today is a very whistle-stop introduction to using Python in this way. So everything in Python. Now, that's the end of my slideshow, and I'm just going to spend the rest of my time now giving you some demonstrations. And I'm going to be sharing this with you. Maybe I could show you that right now before I start, in fact. If you go to this website, oh, not that one, sorry, I'm sorry. If you go to this website here, and I'll put the link in the chat, then you can actually download everything I'm about to show you, the scripts. So first of all, the first thing I want to show you now is if you haven't ever used Python before, how do you get started? Well, if you just search for Anaconda Python on the internet, you should come to this link, anaconda.com. This is a packaged up version of Python that has all of the important packages that you're going to need. So you simply download and install Python from that link. Okay, very straightforward. It works on a Mac, on Windows, on Linux. After you've done that, you're going to want to launch the Jupyter Notebook. And so we're going to spend the rest of our time just looking at this Jupyter Notebook. So when you open Jupyter Notebook, you are presented with a screen like this. It's basically a file browser. And within here, you're able to generate scripts. So if I just click New Python 3, it's going to open up a completely empty Jupyter Notebook. So the first thing I'm going to do is I'm going to rename this script, my first script. And within this block, this web interface, I can now write and execute Python commands. For example, I can print hello. And I type my commands into a block, and then I shift enter to run that block, and it executes that code. I can create variables. So A equals 1, B equals 2. And I can do things, mathematical operations. For example, I can print A plus B is 3. Or I can print A times B is 2. And this is the environment, okay? Now to do anything you can do very simple things in Python, but to do anything sophisticated, you need to start to use packages and libraries, I should say. And so the first thing you need to do in Python is to import NumPy. NumPy is a library of mathematical functionality, basically. So if I import NumPy as NP, I now have this thing called NP, which has a whole bunch of very useful mathematical commands, essentially very similar to what you have in MATLAB available to you. So just to give you a demonstration, let's first of all create an array of numbers, 1, 2, 3. And let's assign that to a variable called x. So x equals NumPy array 1, 2, 3, print x. And you can see it's obviously it's done that, straightforward. Now I can do mathematical operations on that NumPy array. For example, I can multiply it by 2 and 246. I could raise it to the power of 2, 149, and anything you want, right? Divide it by 1 divided by x, 1 1/2 a third. Okay, so what you want to do in Python is you want to use NumPy arrays to store your variables. I'll just show you another thing. Very common thing you want to do is create a large array of values between some limits. So for example, let's say time is going to be NumPy a range 0, 10.1, 0.1. What does that do? Let's find out by printing t. So what that did is it created a NumPy array in the variable called t that has the values from 0 up to 10 with an increment of 0.1. And so that's a very useful thing to be able to do, create a list of numbers basically on a grid like that. Now I could also calculate the sign of t in this way. So y is NumPy.sign of t, and those are my y values. Now what would I would now like to plot my sine wave and see what it looks like. So to plot something, I need to import another library, which is called matplotlib.pyplot. So I import matplotlib.pyplot as PL. And now I have a function pl.plot t against y, and that lets me plot my sine wave. Okay, so that's a very basic whistle-stop introduction to how to use a Jupyter Notebook and how to use these two libraries, NumPy and matplotlib. And you can make very beautiful plots here. You can do all kinds of things like that, for example, and continue to refine it. But I won't spend too much time on that. So hopefully that was a useful introduction. Let me just perhaps check in at this point in time. Am I coming across clearly? Are there any problems with the way I'm delivering this? Too quick?
I think it's good. Andrew, you can go ahead.
It's all good? Okay, then.
All good, all good.
Thank you. All right, well, I'm going to carry on then. Let's move now to the case of coding up a model. So one of the things that we often use in conceptual hydrological models is a so-called bucket model. And the idea here is that you take a component of a system, like, for example, the soil profile, and you simplify it so that you can represent it as a bucket. So, for example, if I'm using this bucket to represent the soil, then Q in, this inflow might be the infiltration rate, and this outflow might be the drainage downwards towards an aquifer, you know, that might become groundwater recharge. So it's the soil drainage. And S, the storage in the bucket, represents the storage in the soil. So this is a very simplified representation of a component of a hydrological system. So I have my inflow, Q in, I have my outflow, KS. So my outflow is assumed to be linearly proportional to the storage in the bucket. And that's why we call this a linear reservoir or a linear bucket. Okay, so let's see if we can code up a solution to this linear bucket problem. Now, the first thing you have to do is derive the equation that describes this system, which you do by looking at the water balance. So the change in storage equals inflow minus outflow. When you do that, you derive this ordinary differential equation, this one here, that says that the change in storage with time, ds by dt, is equal to Q in, which is the inflow, minus Ks, which is the outflow. So that's what we call our governing equation. And if we solve that equation, we will solve for S, storage, as a function of T, time. And then we'll be able to plot storage against time on a graph. Now, just to start with, let's take the very simple case that we have no inflow, so Q in equals 0. And in that case, we can integrate this equation, and the solution looks like this. So we have storage as a function of time is equal to the initial storage times the exponential function of minus KT. Right? So what we'll try to do now is just solve this equation and plot the result for some values of S0 and K. So how are we going to do this? The first thing we're going to do, again, is to import our NumPy library and our matplotlib library so that we can do the mathematical functions and then plot the output. The next thing we're going to do is create a time grid. This is an array of time values, which I've done here. So if I just print that, you can see that my time values go from 0 all the way up to 20 with a regular increment of 0.1. Okay, and that increment is set by this parameter dt, and the maximum value is set by this parameter tmax. So that's very straightforward. Hopefully, we're creating an array of time values there. Next step would be to define the model parameters. So in this model, the parameters are S0 and K. So I should also just make Q in 0, which I'm not using at the moment. So let's just say S0 is 2 and K is 0.5. I've assigned those parameter values. And now I need to somehow implement this equation to calculate S. So the way to do that, simply write it out. So S is equal to S0 multiplied by the exponential function minus K times T. Okay. Basically just writing that equation out directly, right? Nothing too complicated there. I'm also going to write out the outflow. So the outflow is K times S. So let's just simply write that down, K times S. Now let's execute that block and see what happens when we plot the result. And there it is, okay? So in this block of code here, I have a slightly fancy plot. I'm doing 2 subplots, subplot 1, subplot 2. And in the first plot, I'm plotting the storage against time. As you can see, storage against time. And in the second plot, I'm plotting the outflow against time, or the discharge. So you can see that they both look very similar. This is a bucket that is having no inflow, and it's just draining down from some initial storage value. All right, so that's a draining bucket. Hopefully that was fairly straightforward. Now, what we'll just quickly do now is we're going to look at, when you do modeling, you're going to need to use fundamental programming concepts. And there are 3 really important concepts that you need to understand if you don't already. The first one is the concept of a function. So a function is where you take some code that does a particular job. For example, you could take this code here that calculates the storage and the outflow, and you put that code into a function so that you don't have to keep writing it out. And then when you've written your function, you're going to send in some inputs and run the function and then generate the outputs. So this is a really important concept. It's really important that you use functions when you are coding. A function in Python looks like this. So you define the name of the function here. This is the name. You define the inputs to the function here. For example, we might have K and S0 and T and time. And then we're going to do something in the function. For example, we might calculate the storage like that. And then we're going to output something from the function. So what we're going to output, the storage, S. So that's a function that actually evaluates the solution to this bucket problem, right? But more broadly, I just want you to understand the concept of functions, taking inputs and producing outputs. The second fundamental concept is looping. So whenever you have to do something repeatedly in a function, then you should use a loop. A loop is simply going to repeat that chunk of code however many times you ask it to do that. Okay, so you can use a counter to tell it how many times to do it. Here's some code that basically does a loop, repeats something 10 times, and every time it's going to increment the value of I. So if I just print I here, you can see it's printing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times the value of I. And because Python uses zero indexing, the first value of I is 0 and the 10th value is 9, which is a bit confusing. You just have to get used to that. Finally, the third fundamental concept is conditionals. This is where you want to do something or make a decision based on whether something is true or false. So in this case, your code is going to either do execute action 1 or action 2, depending on the condition. For example, if name equals Andrew, print hello Andrew, else print who are you, question mark. Okay, so now that's a conditional. If I say name equals Andrew and I run that block, it prints who are you, and that's because I forgot to, I used a capital A. If I put name equals Andrew, it's going to say name is equal to Andrew, that's true, so execute this block of code. But if I put John, it's going to say name does not equal Andrew, so don't execute this, go to this part, and it says who are you, okay? So basically, those are the three fundamental concepts that you must get your head around. Not that difficult, but really important. And when you can do those, you can start stitching these things together in sophisticated programs. So let's quickly now take some of those ideas and attempt to solve the same problem again, the bucket problem, but this time we're going to solve it numerically instead of using integration. And we're going to use what's called Euler's method. Euler's method is a very simple numerical method which says the storage at the next time step is equal to the storage at the current time step plus the slope ds by dt times the time increment. So basically assuming that storage is changing in a linear manner over a time step. And what you'll notice is this ds by dt term in this equation is given by the governing equation, right? We have an equation for it. ds by dt is q in minus ks. So what we're going to do is we're going to write a function to evaluate that term, ds by dt, and then we're going to use it in the Euler's method here. So let's do that. So here we are. We want to write a function now to evaluate ds by dt. So I've started it. I've said we'll call it model fun. And the first thing we can do is we can say that the output from this function is going to be ds by dt. So I'll just call it ds dt like that. That's what the output is. And what's the input going to be? Well, the input's going to be everything on the right here. So sorry, everything I need there to evaluate ds by dt. So that's going to be q in, k, and s at the current time step. In fact, since s is the dependent variable, I'll just put it first because it's better to do that. In fact, I'm going to put them in this order, s, k, q in, like that. So I've got 3 inputs, and then inside the function, I need to evaluate ds by dt. So ds by dt is equal to, I just go and look at the equation one more time, simply this thing, q in minus k times s. So let's just type that out. Q in minus k times s. And hopefully that function will work. Now in this block of code, I've set up a loop. This is a loop that will go through every time step. And it will calculate storage at the next time step based on storage at the current time step. You know, this is the Euler equation again. This is this equation. So let's just see if that runs. It runs. And now I'm going to plot the result of that calculation. And what you can see here is this is a graph with two lines on it. One is red and one is blue. The red line is that original solution that's so-called the analytical solution. And the blue line is the new solution that I just calculated using Euler's method. And you can see that they're the same. So that just confirms that my numerical method is consistent with the analytical solution. So there are no problems. Now, the thing about the numerical method is I can now look at non-zero values for Q in. So for example, I could just set Q in equal to 2. And let's run the model again. And now what happens is my storage actually starts to increase and it levels off at 4 cubic meters. And that's because I'm now putting more water into the bucket. So it's got to start to fill up. When it reaches 4, the inflow and the outflow are the same. So it's at steady state conditions. Another thing I could do is I could actually say, let's have inflow at the beginning and then turn it off after, let's say, 2 hours. So I'm going to use an if statement here. If the time at the current time step is less than 2 hours, let Q in equal 2, else let Q in equal 0. So now I have inflow for 2 hours and then it stops. So let's see if that works. So what do we see now? We see the blue line, again, the numerical method. So initially the storage is increasing in this bucket because I'm putting all that water in. But then after 2 hours, I stop and the level just starts to drop again. And eventually it drops down to the same level as the red line, which is where we had no inflow. So that was a very, very quick run through coding up a linear bucket. But actually, those concepts are very much applicable when we start to put together much more complicated models. So I'm going to stop here and I'm going to jump now to a more sophisticated model. So let's just close these ones down. And let's go and look at the HPV model now. And the HPV model looks like this. This is another conceptual hydrological model. It's quite common and popular. And it's a series of 4 buckets, basically. So we have a snow bucket, soil bucket, a fast and a slow reservoir. The fast and slow reservoir might be, for example, the river and an aquifer. And precipitation is coming in at the top and it's getting passed in between these buckets in various ways. We simulate evaporation from the soil. We have partitioning of the water between the fast and the slow reservoir. And then eventually we combine all of that water together to simulate the discharge from the watershed. Okay, it's a very simple model. Okay. Now it's got, if you look at these red things are all of the parameters in the model. So for example, the temperature threshold for snow versus rain, the field capacity of the soil, the fraction of water that goes to the slow versus fast reservoir, some routing parameters K1 and alpha, and so on. Okay, so that's the model. This has been coded up in Python. I'm not going to show you the code, but we're going to run it. Okay, and we're going to run it for a watershed in Alberta. This is one of Khaled's, Dr. Akhtar's watersheds, the Bow River watershed in the foothills of the Rocky Mountains, or I guess in the Rocky Mountains, I should say, in Canada here. So here we go. Let's just run the model and see what happens. So I'm importing the libraries first of all, and as well as these NumPy libraries, I'm also importing some other libraries, including this HPV library, which is the code that I've written up for the HPV model. We're going to tell it to look at the Banff Basin. We're going to assign all these different parameters values. So just take arbitrary parameter values for each one. Then we're going to load some observed streamflow data for this watershed. And now we're going to run the model with this line here. So this is going to run the model, and it's going to save the outputs into some of these variables. Should take about 5 seconds. There we go. Let's run. And now we can plot the output of that run. So here we go. This is this may look very complicated, but basically I'm just creating a figure and I'm plotting the simulated data against and the observed data on the same graph. And this data set runs from 1950 to 2013, I think. So it's hard to see on that scale. So let's just change the start and end date. Let's look at the period 1998 to 2001, 3 years. And now we can see this in more detail. So here we have these, I'm just going to mute somebody. I think somebody's, yeah, here we go. That's better. So we have the dotted points, which are the observations of streamflow, and we have the blue line, which is the simulation. And so the very first observation I would make about this model is it's kind of reasonable. It's getting the peaks in the right time, and it's getting the lows at the right time. Maybe that's actually a good model, or maybe it isn't. It depends on what you're trying to do with the model, doesn't it? So looking more closely, I'd see that in 1998, the model drastically overestimated the peak flow. So that might have led to somebody issuing a flood warning, and then there was no flood. In 2000, it did quite a good job. In 1999, again, it overestimated the flood peak. So what we could just quickly do is we could look at how one or two of these parameters affects the model. And let's, for example, look at the PM, which is the precipitation multiplier. So maybe we have our rainfall data and our snowfall data is actually underestimating the real snowfall. So let's go ahead and make that 1.5. Let's run the model again. And what you can see now is that the stream flows increased quite a lot. So that in fact made the model worse. That particular parameter is not something we should have done. Maybe I should actually make it lower. Let's maybe make it 0.75. See what that does. Run it again. And now we actually get the peaks a bit better, but we're not doing a great job on these lower flows. So that's, you know, not great. Now we could spend the next hour just playing with these parameters and seeing what does what. We won't do that, but let's maybe just try the temperature threshold. What this one does is if you make this lower, you're going to get less snow and more rain. So let's make it -1 degree centigrade. See what that does, if anything. Doesn't look like it did too much. Maybe let's just make it higher and see if that does anything. 1 degree centigrade. And again, I think that actually did improve the model a little bit. Brought the peak down a bit. We're still doing an okay job here. So at this point, the best way to proceed with this model would be to try to do some automatic calibration. So I'm just going to try and demonstrate that now using this notebook simple calibration. What this notebook does is it's solving exactly the same problem as we did before. And I'm running it and saving the uncalibrated result in a variable called flux UC here. And then what I'm going to do in this block of code is I'm going to actually, oh, sorry, I'm just going to plot that result again. We've seen that already. But now I'm going to do an optimization. And the way the optimization works is you define upper and lower bounds for each parameter. So for example, precipitation multiplier, I'm saying somewhere between 0.5 and 2. And all of these other parameters are also varying. So I define the parameter bounds. I define the start and end time for calibration and validation, and also spin up. So spin up is basically a year or a period of time where you're not calibrating the model, and then you start to calibrate, and that's it basically. So let's just load those dates. Let's just run the optimization. And what this is doing is it's running that model many hundreds of times and changing the parameters and trying to minimize some error function that describes the difference between the observations and the simulations. Okay, so it did that, and it's come up with this new set of parameters that look like this. And what we can do now is we can run the model with the optimized parameters. We can calculate some statistics. This is the root mean squared error. And then we can plot the result. So let's see if it did anything good. So in this graph here, what we see is the blue dots again are the observed streamflow. The orange line is the original streamflow simulation that was uncalibrated. And the green line is the calibrated streamflow. And actually, I only calibrated this for this hydrological year 2000. So this is the hydrological year where we did the calibration. And these other years are kind of validation. So what you can see actually is it did do a much better job at getting the peak in 1998 and 1999 when I calibrated it, which is very encouraging, right? So I think that's pretty much what I wanted to show you. What we could do is play around a little bit more with the calibration if we want to try to improve it more. For example, at the moment, I'm optimizing all of these parameters, and I guess I am not optimizing the precipitation multiplier. I think if I do this, it will do that. Let me just try to, yes, okay. Hang on, let's try again. Let's just restart and rerun this. So what I've done is I've added another parameter to the calibration, so it may now do an even better job. Let's find out. So you see it's modifying the precipitation multiplier. It's going up. It's at 2 at the moment. Wow, it really wants it to be high. This is slightly worrying. Still trying to calibrate, trying to find the optimum, and hopefully soon it will finish. Okay, so let's see the result. That's a much worse result. Okay, that's a strange, that might seem very strange to you. I added a new parameter and I calibrated the model, and it actually gave me a much worse result. But and that's because I've really got too many parameters now that I'm optimizing. You need to, that's why it's important to calibrate things in a sensible way. So you don't want to, you don't want to include too many free parameters because it might just get stuck in some bad solution space. I'm going to try again. I'm going to try, let me just see if I can perhaps calibrate just a couple of parameters this time. I'm just going to pick, I'm commenting these, whoops, parameters out. So now I'm just going to try and calibrate 3 parameters, and let's see if that works. Better or worse than before. Is it going to work? Ah, it's not working. It's not happy. Why not? Oh dear, that's a shame. Okay, unfortunately, this is not happy. It's not letting me do that. Okay, let me try something else quickly before I give up on this. Pn equals Pn. I just want to calibrate the first, second, so 0, 1. What was the other one I did? Oh, well, let's just do the first 2, right? 0 and 1. dear. Sorry, I'm having a hard time now. I think, oh dear. Let's just do this again. Okay, we're doing the standard calibration. What I'm trying to do is to reduce the number of parameters that I'm calibrating, and to see if I can get a better result by looking at less free parameters. Let's just see. This should be the original result one more time. Again, that was the quite good calibration result. Okay, I can knock a parameter out by simply assigning it the default value. So let's do that. 0.1, 0.1 and 0.3, 0.3. Let's just do that. I've knocked out 2 parameters, so those should not be changing now. Restart run all, and let's see if the result improves. And the result did not improve. In fact, it's really done nothing. So it seems like these parameters that I just commented out are actually really important. So we better not take those ones out. Those are really important to get a good calibration result. Let me take something else out, and then I will, let's try taking this one out. Oh dear, that may also, let's just do it one more time, sorry. It's just running, optimizing. Yeah, okay, it's still not working. All right, well, I've failed to demonstrate, unfortunately, that particular aspect of the model. But anyway, hopefully this has been somewhat useful to understand the process of model calibration optimization. Is it going to run through this? There we are. That's my calibrated result. So that's basically all I wanted to show you today. I've actually finished early. Oh no, I've finished pretty much perfectly on time, I think.
No, Andrew, thank you. You are on time. So
okay.
That's it. And I was also learning while we discussed those things. There are lots of things, and you brought very interesting issues, like in practically most of the cases, what we used to do, we used to use a cookie cutter model or something like that. But there is an opportunity to learn the coding and also to implement that so that you can customize your model as per your requirement. And that is very important to foster your career, and also if you are interested to be in academia, or if you are if you want to do some research, so that's the very important thing to do. So thank you, Andrew, and it's great that we are able to have you in that meeting, and I think everybody learned a lot. Before going to the Q&A session, it's up to you, it's optional. If you guys want to turn on your camera for a while so that we can see each other, that would be great. So if you can, please turn on your camera, maybe for a minute or so. I'll jump to the question. So the first question that I received, Andrew, is saying, like the question is, among Python, R, and MATLAB, what would be ideal for a graduate student without extensive coding experience? So what do you suggest?
Right. If you're starting from scratch, I would personally recommend Python, because Python is essentially, Python can do everything that MATLAB can do, but it's freely available, and there's a lot of free learning resources around Python. in particular on YouTube, on websites like Software Carpentry, and on things like LinkedIn Learning, and any number of places that you can get really high quality lessons. And so for that reason, I think it's the easiest thing to learn independently. Also, it's freely available, unlike MATLAB. So that would be my recommendation.
Okay, no, thank you. So the next question is, as you have shown us the HPV model, are you running the HPV outside of Python environment?
Personally, no, I'm not.
Okay.
Sorry, are you asking in? No, that HPV model that I showed you is fully coded up in Python. Okay. Everything is coded in Python. Okay. If you want to download it, it's available, and at the link I'm providing, and you can, if you know Python, you can look at the actual code itself and see how it's coded up.
Okay. So the next question is, soil is not homogeneous in real situation. How linear model works? It's up to you. It's optional. If you
yeah, you're absolutely right. My work is about soil moisture modeling, and I use Richard's equation for solving the flow equations in the soil. The linear approximation is a very rough method that's used when you want to do something simple at large scales. And it works very well at large scales, but it doesn't work well if you're interested in what's happening, you know, in a particular soil profile. So it's a very simple modeling approach.
Yeah, the next question is similar to this line. Like if you want to add one more sentence, you can add it. Like it's saying that hydraulic conductivity of soil is a function of moisture content and soil grain size. So how linear model works for a professional who works for a consulting company?
That's really good. Yeah, I totally agree with you. And again, it's the same question. What I could have done, I mean, I do spend a lot of time on Richard's equation, and I've coded up Richard's equation in Python as well. If you wanted me to come back and show you that, I'd be very happy to. But again, this is not the modeling I'm doing today has been showing you watershed scale. So we're not looking at the hydraulic conductivity function or anything like that.
I think the next question is along the uncertainty line. So how does you handle the uncertainty of the data, means data uncertainty, and origination, and also how to evaluate and present uncertainty? So I think these are the very valid questions, especially when we are dealing with lots of data and doing lots of communication with the public. So I think that's a very good question.
Yeah, I do too. It's a great question. It's a very important challenge, how to deal with uncertainty. And we have uncertainty from many different sources. Okay, so one of the easiest ones to deal with is parametric uncertainty. So when you don't know what the parameter values are, you can use an ensemble or a Monte Carlo approach to simulate many different outcomes, and then you can present the outcomes as an envelope of possible outcomes. And actually in that HPV model, there's a GLUE, the GLUE method, generalized likelihood uncertainty estimation method. GLUE has been implemented in that model, so you can look at the parametric uncertainty in that way. Input uncertainty is more challenging, but again, you could do ensembles of simulations with different realizations of possible inputs.
Okay, well, thank you. The next question is a little bit interesting. So the question is saying that, is there any reliable model to show the impact of transforming huge snowfall in Canada into very cost-effective renewable energy to the benefit of the world population? So that's an interesting question. And like in summary, like the question is how to bank on huge natural resources snowfall into something never seen before. So like how could we utilize that huge amount of snowfall in Canada for the greater benefit of the world?
Well, that is an interesting question. Khaled, can you might have a better idea about that than I do. I don't know how you could.
Yeah, no, I think, yeah. So I don't know about like how we could address that question. So let's say if we have a huge amount of snow is not bad, and you guys also know it because it actually, like when rain falls, especially the folks who are joining from Bangladesh, you might not have that experience. So especially in the rainfall, you will get the instant water supply around your stream or the downstream of the river. But the snow is a little bit different. So we are getting snow in winter and it's piling up and piling up. And we are getting most of the result during the spring and summer. So that snow actually fed the river system almost throughout the year. So that's where we are utilizing it. And as you are talking about the worldly benefit, then I would say it's a prairie country, so we are producing lots of crops and other things and then exporting. So in that way, actually, we are utilizing that snow. Yeah, I think that's the question. I know it's not an exact question or answer, but I tried to summarize.
Yeah, if I may just add something, I think it's talking about it's probably like the storage of spring runoff, you know, for summer use or something. We do have some of those storage facility in Alberta, but definitely, you know, building an infrastructure would take a lot of, you know, money and cost, and there's a lot of economic analysis that has to be done. And also the tendency in Alberta is, you know, having, you know, intense snowfall rather than having a overall huge amount of snow. Basically, snow is being replaced by rainfall. You know, lately. So yeah, there's a lot of, you know, apart from the technical, there's a lot of, you know, financial and economic analysis has to be done before even thinking about something like that.
Yeah, I think you also mentioned a good point, and like we have lots of reservoirs where we are actually harvesting more or less the snow by reserving that snow melt water and then use it for the agriculture. And also we are running some hydropower plants out of that.
Can I tell a quick story, Khaled?
Sure.
So in the prairies here, the snow melt is very important for agricultural production. And one of the things that we grow on the prairies is lentils. And because of the soils in the prairies, they're very high in selenium. And there was a story that we were selling lentils from Saskatchewan to Bangladesh. Why were we doing that? And because when you eat the lentils from Saskatchewan, the selenium actually buffers arsenic. And some of the people in Bangladesh are drinking arsenic-rich, you know, water that's high in arsenic. So this was a story here for a while that we were helping people in Bangladesh by selling them our selenium-rich lentils. And those selenium-rich lentils would have been grown because of the snow melt that would have recharged the soils. So there you go. I should have said that. That's a good answer.
Yeah, I think that's a very good point. So the next question is, how do you validate the hydrological models developed by Python? So I'm not sure about that question. So probably the question is, how do you evaluate models in Python?
I think the question is, I think it's a good question. Like if I write a model in Python, how do you know it's not complete nonsense? And it's a very good question. And so it's important to validate your model, validate your code, not just validate like the performance of the model, but validate the code. So for example, if you're taking Rich's equation, there are standard solutions to Rich's equation, and you try to reproduce those with your code. In the case of HPV, you could run it and you could compare it to another implementation of HPV that's freely available to make sure it's working. So it's actually a very, very important point. You should if you're writing your own code, you do need to validate it. And if you try to submit to a journal, they might give you a hard time because, well, you wrote this yourself. How do we know this is reliable? So yeah, it's a very good question.
No, thank you. And the next question is, I think you provided some resources, but the attendee wants to know that can you refer a YouTube video or books or some particular Python course website so that people can learn from there?
I can. If you just go to YouTube and search for Python, you're going to get a ton of very good material there. If you have access, I don't know if you have access to LinkedIn Learning. I have access to it through my university. On LinkedIn Learning, there are very good quality Python courses. And I will just point out another thing. I mentioned it before, software carpentry is very nice. And I'm just going to try and find a link for you right now. Here we are. This is the link. Here is an open source book. I'm just putting it in the chat that goes through some really nice Python and beyond Python material.
Okay, no, thank you, Andrew. And probably our last question. So can I perform groundwater modeling for investigating river aquifer interaction using Python?
Well, yes, you can. You could. Well, I mean, you can, but should you? Is a better question. You can, but would it be a big waste of time? If you're doing a project and there's existing software that is perfectly good, like for example ModFlow, it's probably better just simply to use ModFlow and use it in the Python model sandwich in the way I talked about. That's what I would do if I was trying to tackle that problem. So unless you are trying to come up with new ideas about how to simulate that, I think you should probably use existing software, and ModFlow, which is free USGS software, would be, I think, the obvious place to start looking on that particular problem.
Okay, no, thanks. And I got a question. I'm not sure, like, what is the accuracy of the model with compared to other models? So I'm not sure which model that person refers to.
I mean, that's a, yeah. It's not a simple answer to that one. I mean, you know, any model that you have, whether it's a Python model or not, you should look at it closely and assess its accuracy. Yeah, so there are various ways to do that, looking at analytical solutions, checking for water balance closure, and then in the end, looking at how well it performs at simulating your observations. But that's a consideration for any model, whether it's in Python or any other software.
Yeah, I think that's the last question that we are planning to respond today. No, thank you, Andrew. It's a great presentation. And as I mentioned that I was also learning while you are talking, and I think everybody learned something or a good chunk of it from there. And maybe people would be interested in using Python in hydrological modeling. So this is a virtual world. So let's give a virtual pause to Andrew. He actually spent lots of time in preparing that lecture, and especially over the weekend, he woke up early, and I think probably he needs to send his kids outside the home just to be quiet. So no, thanks Andrew very much. And the other thing for all the audiences, you guys also spend lots of time, and especially I know it's 11 o'clock, 11:15 almost in Bangladesh. And the interesting thing is, Andrew, just to let you know that people are joining from lots of places, from Canada, Bangladesh, Germany, and some other countries that I have seen. So thank you all, and please keep in touch, and we'll try to reach you probably to get your feedback that how we could improve, or is there any particular thing that you want us to handle so that we can add a similar type of seminar. And please tune in, and then maybe time to time check the website of BUETAAA-An Alumni Association, you can find our upcoming events, especially the educational events. And if you need further details, you can directly email me, like the email address is in the poster, and I'll also put my email address right away, so that if you have any questions related to the seminar, or if you want to pass additional questions to Andrew through me, then you can send it to me and I can coordinate that. And obviously I'll get back to you as soon as possible. So thank you all for joining, and hope to see you in the next time.